Have you ever really wondered what language your computer actually speaks? I'm not talking about Python or Java. No, I mean the raw fundamental language of the processor itself. Today, we're going to pull back the curtain and demystify assembly.
Okay, so you look at this and it probably seems like total gibberish, right? Some kind of weird cryptic code. But believe it or not, this is one of the most direct and powerful ways to tell a computer exactly what to do. So what's it saying? Let's break it all down.
You know, the absolute best way to think about an assembly program is to see it as a recipe. It's not some complicated novel with a twisting plot. Nope, it's just a super simple step-by-step list of instructions that tells the CPU what to do with a list of ingredients. There's no room for confusion, no guesswork, just pure direct commands.
And that's really why this matters so much. High-level languages, like the JavaScript or Python you might use every day, they're fantastic. But at the end of the day, they all get translated down into something that looks a whole lot like this. So when you understand assembly, you're not just looking at code, you're looking at the actual blueprint for how your software runs on the metal. Think about it. Every good recipe has two main parts, right? You've got your list of ingredients, and then you have the instructions for what to do with them. Well, an assembly program is set up in the exact same way. It's split into a data section for our ingredients and a .code section for our instructions.
The separation is just crystal clear. Over on the left, in the data section, that's where we list out everything we're going to work with. And on the right, in the code section, that's where we write the actual recipe steps. Oh, and those words with the periods in front, like data, those are called directives. Just think of them as little notes for our chef's assistant, which is the assembler, telling it how to set up our kitchen before we start cooking.
So let's zoom in on that ingredients list for a second. The .data section is where we define all of our variables. We're basically telling the assembler, hey, I'm going to need some storage space for these things.
And this is exactly how we do it. First up, we have start val. That D-word thing just tells the assembler to set aside a standard 4-byte chunk of memory for a number, and we're giving it a starting value of 10 right off the bat. Then, for our second ingredient, result sum, we're also asking for a 4-byte space. But see that question mark? That just means we're leaving it empty for now. We'll fill it in later. Now, before we jump into the instructions, we've got to talk about one absolutely crucial concept, the register. So if your computer's memory is like the pantry where you store all your ingredients, a register is like the small countertop or mixing bowl right next to the chef. It's where the CPU does all the actual work, and it's ridiculously fast because it's built right into the processor itself.
All right, we've got our ingredients in the pantry, and we know all about our countertop. Now it's time to actually start following the recipe. Let's walk through this .code section, one line at a time, and see exactly what our program is doing. Our very first instruction is MOVAX start val. Now, MOV is short for move, but it's a little misleading. It's really a copy command. It copies a value from a source to a destination. So here, we're copying the value that's in start val into AX. And AX, that's just the name of one of the main mixing bowls on our CPU's countertop. It's a primary register for getting work done. And here's what that looks like in action. Before we run the instruction, who knows what's in the EAX register? But afterwards, boom, it holds the number 10. And notice how start val back in memory is totally unchanged. We just made a copy. We brought our ingredient from the pantry over to the countertop so we can work with it. Next up, add EAX 74. This one's pretty straightforward, right? We're just telling the CPU to add the number 74 to whatever is currently sitting in our EAX register. That number, 74, is what's called an immediate value. That just means it's a literal number that's baked right into the instruction itself. We don't have to go find it in memory.
So, what's the result? Well, our EAX register was holding 10, and now it holds 84. The addition happens right there on the CPU's countertop, updating our working value at lightning speed.
We finished our calculation. Awesome! Now we need to put the results somewhere safe. So we bring back our trusty MOV instruction, but this time we're copying in the other direction. The source is our EAX register, the countertop, and the destination is result sum, that empty spot we saved in memory a little while ago.
And here we see that final step. We take the value 84 from our countertop register and we store it back in the pantry, our result sum spot in memory. And that's it. The calculation is complete and the result is safely stored away. So, okay, we can do math. That's great. But how do we actually show our result to a person or maybe get some input from them? I mean, do we have to write a recipe for controlling every single pixel on the screen? Thankfully,
No, we don't.
Instead of trying to write those unbelievably complex recipes from scratch every single time, we use a library. And you can think of a library as a cookbook that's just full of pre-written recipes for all the common stuff. The Irvine library, for instance, has ready-to-go procedures for things like clearing the screen, reading from the keyboard, and most importantly, for printing text.
And using this cookbook is a pretty simple three-step deal. First, you just define your text in the .data section. Second, you load its location in memory, its address, into a specific register, in this case, EDX. You can think of this as a rule from the cookbook. If you want to use the right string recipe, the location of your text has to go in the EDX register. And then finally, you just call the right string procedure, and the library takes care of all the hard work for you.
So, we've taken apart a simple assembly program piece by piece. But why does any of this matter, especially if you're, say, a Python or a web developer? Well, because understanding these fundamentals gives you a totally new way of seeing how computers actually work.
So let's do a quick recap of the big ideas. We learned about directives, which are the little notes that help structure our whole recipe. We have memory, which is our pantry for storing our ingredients. We've got registers, the super fast countertop where all the action happens. And finally, we have instructions like MOV and add, the simple, direct actions in our recipe book.
So I'm going to leave you with this question. The next time you write something simple like x equals 10 plus 74 in a high-level language, you now have a little peek at the blueprint underneath it all. You know it's not magic. It's just this elegant recipe of moving data and doing simple math, happening millions of times every second. So what else do you think is going on under the hood?